And now in this lecture we find out the area of the green shape in two different methods. In the drawing we have quarter circle AOB, and we know that line segment AD equals to line segment DO. We also know that this is side OB, that equals to 2 units in its length, and this is again DCB, that is the right angle. Again, our task is to find out the area of this green shape. The area of the green shape is actually the right green triangle DCB. So our task is to find out the area of this green right triangle DCB. So first of all, AOB is a quarter circle, and therefore this is angle AOB, this is a right angle. The radius of this quarter circle AOB is OB, that is 2. And the radius is also AO, that is also 2. So the radius AO equals to 2 units in its length, according to what is given as the question. Point D is the midpoint of the radius AD. That is to say, at point D, the radius AO has been bisected into two halves. The first half of the radius AO is AD, and it is of course equal to the second half of the radius AO, that is DO, and each half must be equal to the radius over 2. That is to say, each half must be equal to AO over 2. So, that is done. We should find out that the radius of the semicircle, we find the radius SR, so the radius R equals to 2, and it is equals to AO, and here at point D, the radius AO has been bisected into two halves. Each half, of course, must be equal to AO over 2. AO over 2 is 2 over 2, that is 1. So the first half of the radius AO is equal to AD, that is 1. And it is of course equal to the second half of the radius AO, that is DO, that is also 1. Here we can implement the Pythagoras theorem on this right triangle ODB. In the right triangle ODB, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle DOB, dB square, this is the square of the hypotenuse, equals to DO square plus OB square. But again, in this right triangle DOB, according to the Pythagoras theorem, the following equation is true: that dB square, that is the square of the hypotenuse, equals to DO square plus OB square. dB is the missing side, so we leave it as it is, so it is dB square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So to that we should find out that OB square OB squared equals to 1 plus 4, that is 5. So OB squared equals to 5. Here we take a root out of this equation and finally get that OB, the hypotenuse OB, is equal to the square root of 5 units in its length. This is the hypotenuse OB that equals to the square root of 5 units in its length. In the next step, we will complete this quarter circle to a circle. We have completed the quarter circle to a circle, and we will extend the radius BO until it touches the circle. And we will define the touching point of the external radius BO with this circle. This point is point P. In the next step, we will extend side CD by side line until it touches the circle. But before that, we will extend the radius AO of this circle by side line until it touches the circle. And we define the touching point of the external radius AO with this circle. This point is point Q. So we extend side CD by side line until it touches the circle. But the question is, well, the extended side CD will touch the circle. This is point P, and this is called PB. When you extend the radius BO is the side line. When you extend the radius BO by side line, the result BP is the straight line, so BP is the straight line that passes through point O, that is the center of the circle, and therefore called PB, that passes through the center of the circle. It is the diameter of the circle. So I can write it down. So PB is the diameter of the circle because it passes through point O, that is the center of the circle. So PB is the diameter of the circle. But the question is, where the extended line segment CD will touch the circle. We will assume that the extended side line segment CD will touch the circle at this point point N. So here we have peripherical angle BCN. So this is peripherical angle BCN. That is equal to 90 degrees in size. Peripherical BCN subtend on chord BA. And again, on this chord called BN. Okay, again, by extending outside CD by side line until it touches the circle, we can do peripherical BCN subtend on chord NB. This is called NB. That is definitely not the diameter of the circle because of the fact that chord NB doesn't pass from point O, that is the center of the circle, and any chord that is not passing from the center of the circle cannot be the diameter of the circle. And therefore, according to our assumption, we have here peripherical. According to our assumption that the extended side CD will touch the circle at point N, we have here peripherical NCB that is equal to 90 degrees inside according to all this equation, but it doesn't subtend on the diameter of the circle because it subtends on chord NB. That is definitely not the diameter of the circle because it doesn't pass from point O, that is the center of the circle. So here we have contradiction to rule 5. Repeat again on rule 5. According to rule 5, any peripherical angle that equals to 90 degrees in its size must subtend on the diameter of the circle. In the going we have a circle, this is peripherical MAN that it is equals to 90 degrees in size, and you can see here that peripherical MAN indeed subtend on chord MN, that is the diameter of the circle. So according to rule 5, any peripherical angle that is equal to 90 degrees in size must subtend on the diameter of the circle. But here, according to our assumption, we have a contradiction. Why? Because we have a peripherical MCB that is equal to 90 degrees inside according to what is given as the equation, but still it doesn't subtend on the diameter of the circle. Why? Because it subtends on chord MB, that is definitely not the diameter of the circle because it doesn't pass from point O, that is the center of the circle, and therefore cannot be the diameter of the circle. So, due to the contradiction to rule 5, we will conclude that the extended side CD will not touch the circle at point N. The next step, we will assume that the extended side CD will touch the circle at this point, point M. Then we will have peripherical DCM. This is peripherical DCM. That equals to 90 degrees in its size, according to what is given as the question, but peripherical BCM subset on chord MB. So this is called MB, that is definitely not the diameter of the circle because of the fact that it doesn't passes from point O, that is the center of the circle, and you know that any chord that doesn't pass from the center of the circle cannot be the diameter of the circle. So we have a contradiction to rule 5. Why? Because we have a peripherical BCM that is equal to 90 degrees inside, and still it doesn't subtend on the diameter of the circle because it subtends on chord MB, that is definitely not the diameter of the circle. So due to those contradictions to rule 5, we will conclude that the extended side CD will touch the circle at point M and not in any other point, because in any other point we have contradiction to rule 5. In order to avoid the contradiction to rule 5, the extended side CD must touch the circle at point P and not in any other point. do it again. We have to find out that the extended side CD must touch the circle at point P and not in any other point due to the convolution to rule 5. So now here we have triangle BCP that is equal to 90 degrees inside, and indeed it's subtend on chord PB, that is the diameter of the circle. Why PB is the diameter of the circle? Because chord PB passes point O, that is the diameter of the circle. So it is exactly according to rule 5, because we have triangle BCP that is the right angle, and indeed it subtend on chord PB, that is the diameter of this circle. So by doing this construction, we're going to do the right triangle DPO. In this right triangle DPO, we know that PO equals to 1. The radius PO equals to 2, according to what we found out. So those two triangles can go into each other. Here, if we implement the Pythagoras theorem on this right triangle DPO, we get that the hypotenuse dp equals to the square root of 5 units in its length. Well, because dp squared, that is the square of the hypotenuse, must be equal to 1 squared, that is 1, plus 2 squared, that is 2, plus 2 squared, that is 4. 1 plus 4 is 5, so dp squared equals to 5. And if we take a root out of the equation, we get that dp equals to the square root of 5 units in its length. Likewise, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, it equals to 2 units in its length, according to what we already found out. So here we can implement Rule 24 in our drawing. A bit quickly on Rule 24. First of all, Rule 24 is for in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. That AO times OB equals to CO times DO. And again, in the drawing of a circle, this is called AB, that intersects with chord CD at point O. So whenever you have two chords that intersect with each other, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement Rule 24 in our drawing. In our drawing, this is called AQ, that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. So, write it down. In our original drawing, we have chord AQ. Intersects with chord CP at point D. And again, now original drawing, we have chord AQ that intersects with chord CP at point D. So all the requirements of Rule 24 are satisfied, and therefore we can implement here Rule 24. According to Rule 24, the following equation is true, that AD times DQ equals to CD times DP. So, write it down. So AD times DQ equals to CD times DP. And again, according to Rule 24, the following equation is true, that AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total is 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, so it is CD times DP. Just like the formula, that the opponent's DP equals to the square root of 5 units in itself. So in total, if we found out that according to Rule 24, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to square root of 5 times CD. Here we divide this equation by square root of 5. And find out that the missing side CD is equal to 3 over square root of 5 units in its length. Okay, this is side CD is equal to 3 over square root of 5 units in its length. So our test is to find out the area of this green shape. What is the area of this green shape? The green shape is actually the right green triangle, DCB. Therefore, the area of the green shape equals to the area of this green right triangle, DCB. We know that the hypotenuse of this green right triangle is DB, it is equal to 5. This is side DC, that is equal to 4 over square root of 5 units in itself. The only missing side is side CB. By implementing the Pythagoras theorem on this green right triangle DCB, we will find out the missing side CB. So we will implement the Pythagoras theorem on this right triangle DCB, that is the right triangle that we are looking for this question, because we have to find out the area of this green shape, and the green shape is actually the area of this green right triangle DCB. So what is the area of this green triangle DCB? According to the Pythagoras theorem, the area of this right triangle DCB, it is equals to dB square, that is the square of the hypotenuse, equals to dC square plus CB square. Here by PT is information for Pythagoras theorem. Again, according to the Pythagoras theorem, in this right triangle DCB, the right green triangle DCB, the following equation is to dB squared, that is the square of the hypotenuse, equals to dC squared plus CB squared. We already found out that dB equals to the square root of 5, and therefore dB squared is square root of 5 squared, that is 5. And it is equals to dC squared. dC is 3 over square root of 5, and therefore dC squared is 3 over square root of 5 squared, that is actually 9/9 plus CB squared. CB is the missing side, so we leave it as it is. So in total, if we found out that according to the Pythagoras theorem, on this right triangle DCB, 5 equals to 9/5 plus CB squared. So here we will multiply 5 by 5 and then we divide it by 5 in order to overcome factor with this number. So 5 times 5 is 25 over 5. We multiply 5 by 5 and then we divide it by 5, so we change nothing. So in this of the equation we have 25 over 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation and finally get that 25/5 minus 9/5 equals to CB squared. So in this of the equation we have 25 minus 9, that is 16/5 equals to CB squared. Or CB squared equals to 16/5. Here we take out of this equation and finally get that the missing sign CB is equal to the square root of 16, that is 4 over square root of 5. So if you found out that the missing sign CB, or again I write this CB, this is the missing sign CB, is equals to 4 over square root of 5 units in its length. Now you can find out easily the area of this DCB. The area of the green shape, that is the area of the green DCB. And again, it is very easy to say that the area of this green shape, it is actually the area of this green DCB. Here the area of the green shape equals to the area of the green DCB. The area of the green triangle DCB equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. And again, the area of this triangle DCB in total equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. So DC is 3 over square root of 5 times CB. CB is 4 over square root of 5 divided by 2. So in total, if you found out that the area of this green shape, that is the area that we're looking for in this question, is equals to 3 over square root of 5 times 4 over square root of 5 divided by 2. 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So in total, the area of the green shape equals to 12 over 5 over 2. So here we move 2 to the denominator and get that in total the area of the green shape equals to 12 over 5 times 2, that is 10. So it is 12 tenths. In terms of numbers, it equals to 1.2 square units in size. Okay, again, if you found out that the area that we're looking for this question, which is the area of this green shape, that is actually the right green triangle DCB. In total, it is equal to 1.2 square units in size. Okay, so we finish with the first method. In the next step, I present to you another way to find out the area of this green shape. Actually, we know that the radius of this semicircle and the radius of this quarter circle is OB, that is 2. The radius is also AO or OA, that is also 2. And at point D, the radius has been divided into 2 halves. Each half must be equal to 1, of course. So in the next step, we will complete this quarter circle to a semicircle. completed the quarter circle to a semicircle. We'll extend radius BO until it touches the semicircle. And we define this point as point P, exactly like we did in the first method. I'll not repeat on the same explanation. We extend line 7 CD, and I already proved in the first method that the extended line 7 CD will touch the circle at point P, not in any other point, due to the contradiction to rule 5. The extended side CD must touch the semicircle at point P and not in any other point. So now, for the dimension in the first method, we have a triangle BCP that is equal to 90 degrees inside according to what is given as a question, and it obeys to rule 5. Triangle BCP that is right angle indeed subset on PB that is the diameter of the semicircle. I already proved in the first method that PB is the diameter of the circle. The semicircle, of course, why? Because it is a chord that passes through point O, that is the center of the circle or semicircle, and any chord that passes through the center of the circle or semicircle must be the diameter of the circle or semicircle. So PB is the diameter of the semicircle. OP is the radius of this semicircle, that is 2. DO equals to 1, and therefore the opponent, so the explain the first method, the opponent must be equal to the square root of 5. So we define angle CP this angle CPB as alpha, and we'll focus on this right triangle PDO, and the right triangle PDO. First of all, AOB is a quarter circle, and therefore this is the right angle. The diameter PB, it's a diameter, it is absolutely straight line. So if we focus on the upper side of the straight line PB at point O, if the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. So this is the right triangle PDO. In the right triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle is equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the small right triangle ADO is similar to the big right triangle PCB. So what those two right triangles are similar to each other? First of all, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles that are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles that are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the three angles of this right small triangle PDO corresponding equals to all the three angles of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you prove that the small right triangle PDO is similar this is similar to this big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PD of this right small triangle PDO or side PB of this big right triangle PBC is equal to side DO of this small right triangle PDO over side CB of this right big triangle PCB, and it is also equal to side PO of this small right triangle POD over side PC of this big right triangle PCB. So write it down. From the fact that the right triangle PDO is similar to the big right triangle PCB, we will derive that the following relationship exists between their sides. We derive that PO or PD, this is side PD, over side PB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle POD over side PC of this big right triangle PCB. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side PO of the small triangle or side PB of the big triangle equals to side DO of the small triangle or side CB of the big triangle, and it is also equal to side PO of the small triangle or side PC of the big triangle. PO is 2. Actually, PO. No, this is PD. This letter is this, so it is PD. PD is equal to 5 over PB. PB in total is 2, it is 2 plus 2, that is 4. And it is equals to DO. DO is 1 over CB. CB is the missing side, so we leave it as it is. And it is equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. So in total, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two expressions are equal to each other. So we will get the equation 1 from those two expressions that are equal to each other. This is to say, the square root of 5 over 4 equals to 1 over CB. So here we will cross multiply this equation, and finally we get that square root of 5 times CB equals to 4. So here we will divide this equation by square root of 5, and finally we get that the missing sign CB is equal to 4 over square root of 5 units in its length. This is the missing sign CB. This equals to 4 over square root of 5 units in its length. We return for long equation. Those two sides are also equal to each other. So we get the second equation from those two sides that are equal to each other. So according to the second equation, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. And again, according to the second equation, this is the first equation, and this is the second equation. According to the second equation, we actually found out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. So here we will cross multiply the equation 2, and finally get that according to equation 2, 4 times 2 is 8, and it is equals to the square root of 5 times square root of 5 plus DC. Here we will open the brackets on this side of this equation 2, and finally get that according to this equation 2, 8 equals to square root of 5 times square root of 5 is 5. And we have here square root of 5 times DC. So do that, we found out that 8 equals to 5 plus square root of 5 times DC. Here we will subtract 5 from this equation, and finally get that according to this equation 2, 8 minus 5 is 3, so 3 equals to square root of 5 times DC. So here we will divide this equation 2 by square root of 5, and finally get that according to this equation 2, the missing side DC is equal to 3 over square root of 5 units in its length. So if you found out that this is the missing side CD, this is equal to 3 over square root of 5 units in its length. Our task is to find out the area of this green shape. You can see that the area of this green shape is actually the area of this green rectangle, DCB. The area of the green shape is actually the area of the green rectangle, DCB. The area of the green rectangle, DCB equals to the base DC times the height to the base, that is CB, over 2. And again, there of the green shape equals to there of the green right triangle DCB, there of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB, that is 4 over square root of 5 divided by 2. So in total, if you found out that the area of this green shape, that is the area that we are working for this equation, in total this is equals to 3 over square root of 5 times 4 over square root of 5 divided by 2. Here we have 3 times 4 is 12, over square root of 5 times square root of 5 is 5 over 2. So here we move 2 to the denominator and get that in total this expression equals to 12 over 5 times 2, that is 10. So it is 12 over 10. 12 over 10 is 1.2. So according to the second method, if we found out that the green shape equals to 1.2 square units in size. So in both methods, we arrive to the same result, that the area of this green shape in total is equal to 1.2 square units in size. So we finish with the second method. In the next step, we'll start the lecture. We start with the repetition of the first method and then we repeat on the solution of this second method. So our task in this question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. Know that line segment AD equals to line segment DO. This is the side OB, this is equals to 2 units in itself. This is angle DCB, this is a right angle. Again, our task is to find out the area of this green shape. The green shape is actually the right green triangle DCB. So we have to find out the area of this green right triangle DCB. So first of all, AOB is a quarter circle and therefore this is a right angle. Likewise, OB equals to OA, they are both the area of the quarter circle. That is equals to 2 and therefore AO, the radius OA is also equals to 2. This is point D. Point D is the midpoint of the radius AO. That is to say the radius AO is bisected into two halves. The first half must be equal to 2 over 2, that is 1. This is the first half AO. And it is of course equals to the second half of the radius AO, that is DO. That is also 2 over 2, that is 1. So AO, D equals to DO equals to 1. In the next step, first of all, solution for AOB is a quarter circle and therefore this is a right angle. Likewise, according to rule 3, this angle equals to 90 degrees in its size. PB is the diameter of the... Okay, but we did a reconstruction, that is to say, we completed this quarter circle to a circle. We extended the radius AO and we defined the starting point of the extended radius AO with this circle, this point Q. Likewise, we extended the radius BO by side line and this touches the circle, this point P. And finally, we extended line segment CD by side line until it touches the circle. But the question is, well, the extended side CD will touch the circle. We assume that the extended side CD will not touch the circle at point P, but in any other point. For example, if the extended side CD will touch the circle at point M, then we have here triangle BCN that equals to 90 degrees in size, and it's obtained on chord BN. Chord BN is definitely not the diameter of the circle, because it doesn't pass from point O, it doesn't pass from point O, that is the center of the circle. Therefore, we have here triangle that equals to 90 degrees in size, and still it doesn't pass us from the center, it doesn't subtend on the diameter of the circle, because NB is not the diameter of the circle, so we have contradiction to rule 5. Because any triangle that equals to 90 degrees in size must subtend on the diameter of the circle. Likewise, we assume that the extended side CD without the circle is point M. Then we will have triangle BCM that equals to 90 degrees in size according to what is given. The question is still triangle BCM subtend on chord BM, that is definitely not the diameter of the circle, because chord BM doesn't pass from point O, that is the center of the circle. Therefore, BM cannot be the diameter of the circle, so we have contradiction to rule 5. Because we have triangle BCM that is a right angle, and still it doesn't subtend on the diameter of the circle. So due to the contradiction to rule 5, we derive that the extended side CD must touch the circle at point P and not in any other point in order to avoid contradiction to rule 5. Now we have here triangle BCP that is equal to 90 degrees in size according to what is given in the question, and triangle BCP indeed subtend on chord BP, that is the diameter of the circle. Why chord BP is the diameter of the circle? Because it passes from point O, that is the center of the circle. And again, we don't have contradiction to rule 5 anymore, because we have triangle BCP that is right again, and it's obtained on chord PB, that is the diameter of the circle. Okay, so here we have some indication before. PB is a diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And therefore, this is a triangle POD, this is the right angle. So here we implemented the Pythagoras theorem on this triangle PDO, and according to the Pythagoras theorem, PD square equals to OD square plus OP square. But first of all, we implemented the Pythagoras theorem on this triangle DOB. This triangle DOB, dB squared, that is the square of the hypotenuse, equals to dO square plus OB square. And again, in this triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to dO square plus OB square. dB is the missing hypotenuse, so we know what it is, and it equals to dO square. dO is 1, therefore dO square is 1 square, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, dB squared, that is the square of the hypotenuse, equals to 1 plus 4, that is 5. So dB squared equals to 5. So here we took out of the equation and find out that the missing hypotenuse dB is equal to the square root of 5 units in itself. This is the missing hypotenuse dB is equal to 5 units in itself. So here, you don't have to repeat on the same process, because we have here two congruent triangles. So, and therefore, in this triangle POD, the hypotenuse must be also equal to square root of 5. actually then presented to all 24 and we implemented all 24 in our drawing. Repeat quickly on all 24. All 24 is true in any circle, so in any circle we call the AB intercept, we call CD at point O, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 24 in our drawing. In our drawing, this is called AQ. That intercept we called CP at point D. Again, called AQ, intercept we called CP at point D. So all the requirements for all 24 are satisfied, and therefore we can implement all 24. And again, now original drawing, we have called AQ, that is intercept we called CP at point D. So here we can implement all 24. According to all 24, the following equation is true, that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total equals to 1 plus 2, that is 3. So DQ is 3. And again, AD is 1, DQ is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. DP is equal to 5. Again, CD is the missing side. And DP is equal to 5. So in total, if you formula 1 times 3 equals to CD times equal to 5. 1 times 3 is 3 equals to the square root of 5 times CD. Here we divided this equation by square root of 5 and found out that the missing side CD is equals to 3 over, 3 over square root of 5 units in its name. This is the missing side CD is equals to 3 over square root of 5 units in its name. The next step we implemented the Pythagoras theorem on this line DCB. According to the Pythagoras theorem, this diagram DCB, dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. This green diagram DCB, according to the Pythagoras theorem, dB squared equals to DC squared plus CB squared. The hypotenuse dB equals to the square root of 5, therefore dB squared square root of 5 squared, that is 5. And here we have this equals to DC squared. DC is 3 over square root of 5, and therefore DC squared is 3 over square root of 5 squared, that is 9 fifths. Plus CB squared. CB is the missing side, so we leave it as it is. So in total, if you found out that 5 equals to 9 fifths plus CB squared. Here we multiplied by 5, we multiplied 5 by 5, and then we divided by 5 in order to overcome part of this number. So 5 times 5 is 5 over 5. And it is equals to 9 fifths plus CB squared. Here we subtracted 9 fifths from the equation, and finally found out that 25 plus 9, 25 fifths plus 9 fifths equals to 25 minus 9 over 5, and it is equals to CB squared. 25 minus 9 is 16, so in total in this end of the equation we have 16 fifths equals to CB squared. Here we took out of the equation and found out that the missing side CB is equals to the square root of 16, that is 4 over square root of 5. And again, in total we found out that the missing side CB equals to 4 over square root of 5 units in its name. This is the missing side CB equals to 4 over square root of 5 units in its name. So the area of the green shape equals to the area of this green rectangle, DCB. The area of the green shape equals to the area of the rectangle, DCB. And the area of the rectangle, DCB equals to the base DC times the height CB over 2. Again, is equals to the base DC times the height CB over 2. DC is 3 over square root of 5, CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, over square root of 5 times square root of 5 is 5 over 2. Here we move 2 to the denominator, and finally we know that this expression equals to 12 over 5 times 2, that is 12 over 10. 12 tenths. 12 tenths is 1.2. So if you found out that the area that we are looking for this equation, that is the area of this green shape, in total it is equals to 1.2 square units in size. So we finish with the first method. In the next step, I'll repeat on the repetition of the second method. Repeat on the solution of the second method. In the first method, we only found out that the radius of this quarter circle equals to 2. So OB equals to OA, the above the area of the quarter circle, equals to 2. AU equals to 1, D also equals to 1. At point D, the radius of AU is dissected into 2 halves, each half equals to 1. In the next step, we completed this quarter circle to a semicircle, and the AOB, this is again AOB, this is a right angle because AOB is quarter circle, and therefore angle AOB is a right angle. This angle equals to 90 degrees according to rule 3. Because we know that PB is the diameter of the semicircle. It is a chord that passes from point O, that is the center of the semicircle. We know that any chord that passes from the center of the semicircle or circle must be the diameter. So PB is the diameter, it is absolutely straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the areas must be equal to 180 degrees according to all 3. So which areas we have in the upper side of PB at point O, we have this angle that is right angle plus this missing angle, so that they must be equal to 180 degrees according to all 3. Therefore this missing angle must be equal to 90 degrees in size. So in this right triangle POD, 2 square plus 1 square equals to PD square, and therefore PD equals to the square root of 5. As I already mentioned in the first method, we extended side CD or isomet CD by side line, and I already proved in the first method that the extended side CD must start the semicircle or a circle at point P and not in any other point. Due to the contradiction to all 5, we must conclude that the extended side CD will start the circle at point P and not in any other point. So, by doing the construction, we get the right triangle PDO. As I already mentioned before, the hypotenuse PD equals to the square root of 5. In the next step, we find this angle as alpha. So in the right triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this further angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this further angle must be equal to 90 degrees minus alpha, according to the same rule that said that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is the small right triangle PDO. It is similar to this big right triangle PCB. So why those two right triangles are similar to each other? First of all, this is angle alpha, that is the common angle that belongs to both triangles. Angle alpha definitely belongs to the right small right triangle PDO, and angle alpha is definitely belongs to the big right triangle PCB. So angle alpha is the common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both right angles, and therefore they're equal to each other. And finally, those two angles are both equal to 90 degrees also, and therefore they're equal to each other. So if you prove that all the figures of this small right triangle PDO correspond equal to all the figures of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. And again, if you found out that the small right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PD of this small triangle PDO over side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle PDO over side PC of this big right triangle PCB. And again, from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. That PO over PB equals to CD over CB equals to PO over PC. It is PD over PB equals to D over CB equals to P over PC. PO equals to the square root of 5, PB equals to 4, DO equals to 1, CB is the missing side, so it is, and it is equals to PO, that is 2, and this is side PC. Side PC in total equals to the square root of 5 plus CD. And again, CD in total equals to the square root of 5 plus DC. This is side PC. PC in total equals to the square root of 5 plus CD. And PC in total equals to the square root of 5 plus DC. So in total, if you found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so we can do the first equation for those two sides that are equal to each other. So according to the first equation, if you found out that the square root of 5 over 4, the square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, if we found out that 4 times 1 is 4 equals to the square root of 5 times CB. So total according to equation 1, we found out that the square root of 5 times CB equals to 4. Here we divided the equation by square root of 5 and found out that CB equals to 4 over square root of 5 units in itself. This is the missing side CB. This equals to 4 over square root of 5 units in itself. Those two sides of the equation are also equal to each other, so we can get the equation 2 from those two sides that are equal to each other. That is to say, according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. So according to the second equation, we found out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation 2, and we found out that 4 times 2 is 8 equals to the square root of 5 times square root of 5 plus DC. Here we open the bracket of this side of this equation 2, and we found out that 8 equals to the square root of 5 times square root of 5 is 5. And we have here square root of 5 times DC, that is square root of 5 DC. So total according to equation 2, if we found out that 8 equals to 5 times square root of 5 times DC. So here we subtract 5 from this equation 2, and we found out that 8 minus 5 is 3, and 3 equals to the square root of 5 times DC. Here we divided the equation by square root of 5, and found out that the missing side DC is equals to 3 over square root of 5 units in itself. So, okay, this is the missing side CD is equals to 3 over square root of 5 units in itself. So the area of the green shape equals to the area of this right triangle DCB, and the area of this right triangle DCB equals to the base DC times the height CB over 2. And again, in total, the area of the green shape equals to the area of this green right triangle DCB, and the area of this right triangle DCB equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC equals to 4 over square root of 5, and CB equals to 4 over square root of 5 divided by 2. Here we have 3 times 4, that is 12. Square root of 5 times square root of 5 is 5 over 2. So in total, now the region equals to 12 over 5 over 2. Here we move 2 to the denominator, and we found out that the region in total equals to 12 over 5 times 2, that is 10. So in total, this expression equals to 12 times, that is 1.2 square units in size. So in total, we found out that the area that we are looking for this question, that is the area of this green shape, in total it is equals to 1.2 square units in size. So in both methods, we arrive to the same results. Okay, thank you very much.